Communication Level 1, Second Edition. Latency. Latency is the lag from the time an action is taken until the desired result is achieved. Now, everything has latency. When you order at a restaurant, there's lag from the time you order your food until the time it's ready. When you're sending mail, it takes time for the postal service to deliver the letter to the destination. And when we speak to someone on a conferencing system, it takes time for the signal to get to the person on the far end. When we're dealing with networks, we measure latency in milliseconds or microseconds. A millisecond is a thousandth of a second. It's abbreviated with a lowercase m. A microsecond is a millionth of a second. It is abbreviated with the Latin character mu. It looks like a letter U with a stem on the front. Now, if you're in a technical documentation system or an email system that can't replicate the Latin character mu, it's common practice to just use a lowercase u, and we know what that means. Now, before we get into the latency of an audio-video system, let's keep things in perspective. Let's imagine two musicians playing together acoustically, and let's say these musicians are about 3 meters or 10 feet apart. When the drummer plays, it will take about 10 milliseconds for the sound to travel from the drums to the bass player. The bass player will hear that sound and play in response to it. So in this case, latency at the speed of sound is 10 milliseconds one way or 20 milliseconds round trip. Well, you know what's faster than the speed of sound? A Dante network. If this was a stage and musicians were mic'd up and using in-ear monitors, the total system latency is usually in the 5 to 10 millisecond range. But notice the Dante link can be as fast as 250 microseconds, or a quarter of a millisecond. Certainly, settings at or below 1 millisecond are very typical. On a Dante system, latency is deterministic. What that means is you can decide how long to give your audio or video to traverse the network and play out the other end. On a local network, the latency of a Dante network will be imperceptible by musicians or presenters alike. If we set latency to 1 millisecond, then that is the total latency of the Dante connection. You could start a timer when one Dante interface receives the audio from the host device. The Dante interface packetizes the data, sends it across the network, receives it at the other end, and reconstructs it. Stop your timer when the signal plays out at the other end. To be clear, if we say the playout time will be 1 millisecond, we don't mean 1 millisecond or sooner. We mean it will be 1 millisecond, and we will do it with precision better than 1 microsecond, or 1 millionth of a second, for impeccable phase accuracy. When designing smaller systems, a safe rule of thumb is to allow 0.1 milliseconds per switch the signal needs to hop through. We often call that a network hop. Even if we don't know much about your network switch, if it hasn't been optimized at all, this should be a pretty safe value. Now, as we look at this drawing, you might say, aha, we have 3 network switches. But remember from earlier, many Dante devices have a network switch inside them. So in this case, we'll actually have 5 network switches. And we could safely cover this in 0.5 milliseconds or 500 microseconds. So every Dante device has a default latency setting where we determine how much time we're going to give the signal to get across the network. So what happens if the transmitter and receiver have different latency settings? Dante will always use the longer of the two. Let's build a chart where we have a receiver at 0.5 milliseconds and we have 3 transmitters, one with a shorter time, one that matches, and one that's set longer. In the first case, the receiver is longer, so the receiver's value is used. When the devices match, well, that's a no-brainer. And in the last example, the transmitter's value is longer, so it gets used. Now this can be put to good use when you have signals crossing multiple systems. Let's suppose we have a system on stage all running at a quarter millisecond, so the musicians get very low latency performance. The front of house and PA might be a few switch hops away, so we might set that to a half millisecond latency. Then we have additional DSPs and amps for lobbies and overflow areas. We could set them to 1 millisecond so the switches can traverse many switches. So all connections on stage are running at 1/4 of a millisecond. When we connect from the stage to the main PA, it will use the longer of the two latencies, 1/2 millisecond. Then, when we send the mix to overflow areas, that will happen at 1 millisecond. All predictable, all deterministic. It's worth noting that Dante devices can have different latencies for different connections. In Dante Controller, we'll see a latency tab with separate reports for each combination of devices. We can see how much time is given and how much time it is actually taking. The top device is operating at 1/4 millisecond, the second is operating at 1 millisecond, and the last is running 10 milliseconds. Okay, so let's do a walkthrough of the settings in Dante Controller. If we look in Network View under the Network Status tab, we can see at a glance the latency settings for all devices. Just to the right, I have a single light telling me if there are any latency issues with the device. Green is good, red is a problem, and amber just means there are no subscriptions on the device. Of course, if I double-click on a device, I enter Device View where I can get more detailed information. If I go to the Device Config tab, I can set the default latency for this particular device. Now, different devices will have different latency options. Most of our hardware chipsets support 1 gigabit connections and can achieve 1/4 millisecond of latency. Devices based on our low-cost Ultimo chipset supports 100 megabit ports, and even they achieve a respectable 1 millisecond of latency. When we get to virtual sound cards, you'll find that these may require more latency. Now, the fact that a virtual sound card requires more latency, that's not a networking concern. That is because virtual sound cards are software running in a multitasked environment. Right? The virtual sound card is running on your CPU along with your audio or video applications, and we have to wait our turn as the CPU runs around to all the processes. That's what the extra latency is for. Now, if I look in Device View for the mixer, we can see here I have signals coming from multiple devices. So, when I go to the Latency tab, I will get reports on the network performance for each device. Since they could be in different locations, they might take different network paths with different performance. This is your way to check and make sure that everything is looking good. Interestingly, let's look at these stage boxes feeding the mixer. Here, we can see these devices are set for 1 millisecond of latency. And the chart says I'm averaging 336 microseconds. Now from that, you might conclude that these devices would not be able to support 1/4 millisecond of latency. But indeed, I can tell you these are gigabit devices, and they're all plugged into the same network switch. It should work, right? Well, as we say, try it and see what happens. Okay, so let's change these settings. I'm on the mixer right now, so I'll go to the device config, choose the 1/4 millisecond setting, and click OK to apply it. I'll fast forward as I do the same for the stage boxes. In the Network Status tab, we can now see these 3 devices are all set to 1/4 millisecond. And if we open Device View for the mixer, we'll see the system is indeed achieving the required latency for the stage boxes while still maintaining the 1 millisecond connection for other devices that need a bit more time. Now, how did this happen? Right? We didn't change our network configuration at all. We simply asked our Dante devices to achieve a lower latency. And suddenly, our network packets are getting across in half the time. Well, when you ask for a lower latency, our devices will optimize the packets to achieve the latency you're asking for. And this is but one of many features we do that enables us to back up the claim that if you have a small or medium-sized network, you may not need to optimize your network switches at all. We do a lot of it from our Dante endpoints for you. So let's put this all in perspective of just how fast a Dante system can be. Here I've assembled a collection of gear that will take a mic on a snare drum, get the sound through a mic preamp, across the network, through the mixer, back to an analog out for a headphone amp, all in about 1.44 milliseconds. This Dante rig can actually deliver the sound to the drummer's headphones faster than the sound will acoustically travel to the drummer's ears. Now, video equipment is always slower because of the amount of processing required in video images. but Dante AV still performs very well. We took a signal from an HDMI output, encoded it, sent it across the network, decoded and streamed it out an HDMI port, all in 8 milliseconds. At 60 frames per second, that's still about a half a frame. So of course with a Dante system, audio and video signals are maintained in separate streams. But it's important to us that we keep audio and video in sync on those, right? We want to have lip sync maintained. Dante AV does that automatically, and let's show you how we do that. If we have a signal coming into a Dante AV device, the network transmittal time will be the same regardless of whether the signal is audio or video. The offset in delivery time typically comes from the processing for a video codec, an HDMI chipset, and things like that. So, on the transmitter, we insert an audio buffer to delay the audio to match. And just like that, things are in alignment once more. In fact, if we remember the Video Basics chapter, we showed you the adjustment for the audio buffer settings. So the audio buffer is made available in case you need to make an adjustment based on the system downstream. Let's suppose you're feeding a video wall with an image processor that has a significant amount of latency, but the audio is going directly to an amplifier. If we transmit this with perfect lip sync, it's going to appear to play out of sync, right? So, by providing the audio buffer, you can create the counterbalancing offset so that things will appear to play out properly on that system. But if your system downstream is in time, then you don't have to worry about this. Just leave it alone. Now, just as our audio alignment is very accurate, so is our video alignment. This is key when working with multiple image displays. For instance, if multiple screens are stacked together, or if multiple projections are blended together, the images will all play out, eliminating flickering concerns. So in summary, everything has latency. For Dante, it takes time for devices to packetize the data and get it across the network switches. Dante latency is negotiated between the transmitter and receiver, referencing their default setting. Typically, latency will be set between 1/4 millisecond and 1 millisecond. This is fast enough that musicians and presenters alike will not be affected. A good rule of thumb for a modest system is to allow for 0.1 milliseconds per switch hop. If your transmitter and receiver don't agree on a latency setting, then the system will use the longer of the two. When using audio and video signals together, Dante AV will maintain lip sync even though the essences are separate. Because video usually takes longer to pass through processes, Dante AV delays the audio to match the playout through its components. If you need to manage that offset separately based on the system you're feeding, the audio delay buffer is available for you.